previous video, we got as far as being able to drive values to the 7-segment controller over the axi bus, and there's something wrong in the design. It doesn't actually make the expected changes to the 7-segment display. So to be able to debug this, I could go through and set up a logic analyzer and maybe go through all of that, but really I think the best bet is to be able to simulate this. And the problem is that to simulate this, I can no longer just simply simulate a couple of inputs. I actually need to simulate the way that the 7-segment controller communicates with the system, and that's over the axi bus. So what we've got here is the timing diagram from the Xilinx axi bus, and there's a number of different phases that we're in. So this kind of first phase here is an idle phase, and actually this is reset, and this is an idle phase where nothing's really going on. The next phase of this timing diagram begins right here, and what we see is this is input to the host, or into the slave. And this is an assertion that there is a write address, and that write address is valid. So that's what these two lines here are doing. I don't like this example because this is the same value, but this is really the data that is being written to the memory address. So this is the address, and I get that from its name out here, and this is the data. I get that from its name out there. And the way that this is organized, and this is also input, by the way, and this is input. Basically what we're doing is we have these pair of data lines, and then we also have a pair of valid lines that we're using to assert that the address and the data are valid. There's also a response line, so this is output from the module. These lines are output to say that the value is ready. In other words, that the slave is ready to latch up these values. It doesn't mean that the slave is done. If the slave has a long response time, for example, if we're writing to DDR memory, it may be that there's more than just a handful of cycles here. But what's going on now is that this allows the slave to kind of disconnect from the parent and go handle the write. And then when the slave is done, it's going to assert this last line here, this be valid. And this is telling us that the write has been accepted, it's been complete, and we're ready to accept another line. And so at the very end here, we're back into an idle state, and the master is ready to accept the next command. And so however many different clock cycles this took is dependent on the hardware that we're writing to. If this is very fast hardware, this could be as short as 1 clock cycle, and if it's very slow hardware, for instance writing to a NAND flash, this could take quite a bit longer. So this kind of gives us the idea of what we've got to be able to do in the simulation. So this is a simulation that I've already built to give an idea of how you drive values over the axi bus. And just like every other simulation, we start off with our time scale and our default net type. If I was really trying to get an accurate timing diagram, I'd want to set this to be the speed of my actual clock. And it looks like maybe I actually have at this point. If this is 1 nanosecond, this will give me that 10 nanosecond clock that corresponds to the 100 megahertz bus clock. This is our reset signal, and the axi reset is actually reset n, so that it drops from a low, meaning it is reset, to a high, meaning it is not reset. Okay, so those two symbols kind of get bound up to our clock and our reset, and then all of the rest of these symbols, all of these registers, are the inputs. We go back over here. This is the top level 7-segment controller that was generated by the IP wizard, and we see that there's a whole bunch of input wires here. Those are all going to be driven by the axi master, and in this case my simulation is serving the role of the master. Any place I have a wire, that's going to be output, and in my simulation, it's because that wire is being driven by the slave to my simulation, that's going to be a wire. So all of these registers correspond to registers, all of these wires correspond to the outputs from the module, and we just kind of roll through. And to be honest with you, what I did is I went to the user level, the one below this, and I copy and pasted all of these values. They're the exact same values with the exact same function. In other words, they're passed through from this top module down to this user module. The nice thing is the wizard created all of these different names, all these different comments to go with the wire names. So the next thing I did is I took the instance of this top level module and I connected all of the output, or all of the register signals, with either the registers or the wires that we created up above. Okay, and then in my simulation, oops, back to the simulation. So I just kind of connected all the wires. I even added the two ports that we created, the anodes out and the cathodes out. And what I did next is I created this task called write axi register. And to be honest with you, once you have this thing written, you might want to leave it around somewhere so that you can reuse it. A task in Veralog kind of serves the same role as a procedure would or a function would in another language. And the idea is I can use this so that it looks like a function, but really it's just going to do all of these instructions for me. So in this case, what we've got going on is we're going to do a write, and I have an input for an address and an input for a data. The address here is only 4 bits wide because that's the size of the number of registers we created. So we created a device that had 4 registers, and so only the most 2 significant bits of this address are going to be used. The lowest 2 least significant bits are going to be used for the byte address, which are always going to be 0 for us. I add a monitor statement so that anytime either of these values changes, we can track that be valid. Remember that be valid is the indication that the write has been finished. I do a display to say that we're beginning a write. We wait for the negative edge of the clock, just like we saw before in the timing diagram. We assert that we're going to be writing. We latch up the address and the data, and we turn on the 32-bit word store here. We wait until be valid becomes 1, indicating that the write has been accepted. And then we wait until be valid drops to indicate that the write is complete. And then we display messages to that effect. And so now, with this in place, this kind of serves the role that writing to these registers with C language would serve. And so then my simulation starts to look like this. And so we're going to be able to pick a register. In this case, this was register 0. This would have been register 1. This would be simulating a BCD value. Notice here that we're putting a 1 into our mode bit, and I have some stuff on the upper bits that would have corresponded to a bitmap value, which we should see overridden by this axi register, or by this BCD value. So at this point we should be able to hit finish, and then we should be able to see what the output looks like. Let's take a look and see what we get. So the simulation finished. It hit the finish line here, and we can take a look at the waveforms. And I'm going to zoom out. And most interestingly, here are the waveforms. Our waveforms are all Z's. That's not what we expected. So when we wrote values here, when I put the mode value in, we expected that to not be all Z's, right? So what I can do now is I can actually get rid of, well, first of all, we could verify that we're writing, and the easiest way to do that really is going to be to go back here to the objects and find the look here at unit under test. That's the interior view of the next module in. Remember, that was the module that we wrote. And I can even go one level further, and I can go into the 7-segment controller instance, and that's the owner of the 4 slave registers. So I was staring at the lack of slave registers, and then it dawned on me that the optimizer would have renumbered everything, because all of the slave registers that we had ended up being bound down here to the different values. So that's okay. That's actually a good thing. What it allows me to do, for example, is I know that I should be looking here at mode and BCD values. So I'm going to add a new divider here just so I can keep track of, this is the top exterior view, and then this is going to be the controller itself. And I'm interested in this particular simulation in simply looking at mode and BCD values. So if I hit restart and I rerun our simulation and I look at the waveforms, look, we can see that the writes are correct. They're working. You know, at the time that the write finished, the mode BCD values appropriately changed, and that means that we wrote correctly to slave reg 1. The mode changed to 1, which is correct. That means we wrote correctly to slave reg 0. So all of that was good. So the fact that these things up here, these anodes out, are still all Z's, tells me that the problem is actually above this module. It's above this layer. So if I take a look back at my unit under test now, we can scan around here and look for any places where the anodes out would be anything other than Z's. Well, we can see here part of the problem is the selected cathodes and selected anodes has been hand-coded, hard-coded to the wrong values. I wonder why that would have happened. Jeez. So what we can do is get rid of that and put the right code back in. So if mode is equal to 0, we're going to choose the bitmap cathodes. If the mode is not equal to 0, it's going to be the BCD anodes and cathodes. So let's go ahead and resimulate. Okay, so we've resimulated, and now that we've fixed that bizarre error, we can now see that the anodes out has changed from all Z's to ZZ0, which that seems kind of unusual. So we can go back here to that top level controller, and let's just make sure, for instance, that when we're moving values out of the anodes and cathodes, that we're moving them out correctly. And it sure looks like we are, right? So cathodes out, selected out, cathodes out, selected, they're all what I would expect them to be. So now, if that's the case, let's take a look at our unit under test, and the signal that should be driving everything here, I'm going to add another divider, new divider, and we're going to have this be our unit under test. And the things that I'm interested in would be the BCD anodes, the BCD cathodes, anodes out, cathodes out, and the BCD value would be what's coming from the BCD controller. So let's take a look at those, and perhaps the BCD controller isn't doing what it's supposed to be doing. And BCD values and mode were already displayed. So what did it do? It didn't actually bring them all over. So let's move so there's anodes out, cathodes out, BCD values. Let's grab BCD anodes and grab BCD cathodes. So let's resimulate. So relaunch. Okay, so it would appear that for this particular time period, BCD anodes is 0,3F and BCD cathodes is 1. So we'd have to work out, I believe, 3F does correspond to one of those values that we saw before. I'd have to work out what number that would be. Let's take a look. So if I go to my simulation, we go to BCD control, look at our BCD to 7. It looks like 3F corresponds to a 0. So that's interesting. So it's going to put a 0 onto digit 1. Well, actually, that's not that interesting. That's a 0 there for digit 1. So it looks like the BCD controller is still working, but now I've got a problem somewhere in that connection between the output, the BCD anodes and cathodes, to B anodes and cathodes, out. Well, the only thing that connects those two is the selected anodes and cathodes. So if I look at selected anodes and cathodes, again, we have to resimulate every time we add something to the waveform viewer. They're correct. So let's see, what could possibly be going on here? Alright, so Xilinx burned me again. I went through the simulation and was staring at it and couldn't find anything wrong. So what I did is I modified the simulation to wait for the anodes out to change to the particular pattern that I was looking for. And when I go to run the simulation now, let me show you what the error is. I really wish someone at Xilinx would sit down and actually use their software sometime. It just seems like there's stuff that just shouldn't happen. I'm going to just let it run until it hits those finish points, because I know that it does. And sure enough, look, there it hit finish. And when I look at anodes out and cathodes out, they look absolutely wrong. Like, there is nothing even remotely close to right about those. But if I expand them, I see exactly the values that I was supposed to see. So remember, Z corresponds to a 0, 1. A 0 here corresponds to a 1 in the original anodes out. This corresponds to 1, 0, 0, 1. Sorry, 0, 1, 1, 0, 0, 1, 1, 0, 0, which would be the equivalent of 6, 6 in hexadecimal. And if I zip down here and look at the original BCD anodes, it is, in fact, 066. Sorry. Again, this is one of those weird times where the viewer here it's showing right here at the very edge that there's been a change, but we don't really see that change. If I move the mouse over here, we see that it is 3F, and there it is 6. If I change my time up here to something small and I say run for just 10 microseconds, we'll see that the wave is actually now 066. There is that change point. So this wave viewer has a couple of quirks in it. I'm not real happy that it doesn't, for some reason, display the high impedance traces correctly. That seems to me to be a little bit of a bug. But having gone through and just kind of tweaked a few settings and double checked a few things, I think this code should be ready to go. I have some confidence now that the values are in fact being written the way I thought that they're supposed to be being written. So the last thing I want to do, I know this video is already getting long, is I want to show you how to update all of these. So in here is the 7 controller file, and here are all of the Veralog files that we have. And all of these import files are the current version of all of the controller files. And so if I go into here and take a look at them, these are all the files that we're currently using in this design. By the way, I'm using a program here called MobaXterm. It's a great way to get all the Unixisms that you like under Windows. If I take a look at the 7 system, I'm sorry, at the IP repo, and I go into the 7 seg controller and look for all my Veralog files, I see that there's a pile of source files in there. And if I were to look at the differences between these guys, there we go, we can add some context to it. This is the only change, and that change was in the top level where we fixed that hard-coded value. So theoretically, I should be able to move this file over into my main project now and rebuild. Okay. So what I'm going to do is I'm going to, since that's the only change, I'm going to CP the files from drive C, Vivado, CMP, the 7 segment, controller, sources, imports, vid, controller, .v to here. That's the only file that had a difference in it. And so now that that's been updated, what I can do now is go back to Vivado, go back to my 7 system. It says that the catalog is out of sync, so we'll refresh the catalog. Ah, there it is, the upgrade selected button. Somehow we had to click on that. Well, I was going to continue trying to figure out what was going on with this Xilinx project, and that was about 8 o'clock this morning. Fast forward 6 hours, 8 hours, it's 4:15 in the afternoon now. I've blown the entire day trying to figure out what the hell was going wrong. Tim suggested at some point that maybe I try using an older version of Xilinx, and I thought, I'm not going to bother doing that. Turns out that on my laptop, when I made the first video, I was using version 2016.2, and on my main computer, I'm using version 2016.4. And somewhere between those two sub-revisions, we're talking about a few months worth of time here, somebody at Xilinx got it into their head that we're just going to make shit break. It's just a fantastic example of why we have to have 15 different versions of the software laying around until we finally find one that works. So this rant, I just can't even begin to describe it. I finally found the issue has to deal with, and I found it by opening the design as an elaboration and looking at the schematic. And what I see is that the in-out ports that I used somehow got translated into simple output ports. And I see that they're created with these O-buffs. And as an O-buff, it's either sourcing voltage or it's sinking to ground. There's no high impedance associated with this. It's just an output buffer. I don't know why Xilinx, in their infinite wisdom, decided to say, hey, you specified a high impedance port there, an in-out port, but nah, you didn't really want that. And in fact, if I bring this file over, this is the exact same schematic, the exact same project that I brought over from version 2016.12. Now, the fascinating thing is, when I compiled it with version 2016.12, and then I copied it over from my laptop over to my desktop, it said, oh, we have to upgrade your design. And I said, fine, go ahead, make my day. That's just great. I expected the bug to come back, but no, because Xilinx in their infinite wisdom preserves a magic setting, the magic, ever famous, make it work setting. Let's see, we can follow this around. Look at that. There is not a single I/O buffer anywhere in this design. 8 hours. 8 hours to find that one stupid difference. So I go around on the internet, I search around, I'm on the Xilinx website, and I finally find an answer record where people are talking about, this is in 2016, people are talking about generating output products as an option that you can kind of randomly click on. And when you do that, it will generate either global or out of context per IP. What the hell does that mean? I don't know. But the idea is, if you go here to your design and we go to, I gotta find it again. we have to go, oh, here it is. So I right click on the design block diagram and I choose generate output products, and sure enough, this one here, the one in 2016.4 that I created in 2016.4, is set for this out of context per IP. If I bring the one that generated correctly and I look at its block diagram, it'll probably be the same. Let's see, design one, go to sources, expand this wrapper, right click here and generate output products. Hey, look at that, it's set for global. Wow, that's just great. So that's the difference. That one option makes these kind of random output buffers show up for no reason whatsoever. So then I thought, great, I will go ahead and I will click on that option and all will be well. And so look, it's thinking real hard. Click on generate, it's going to generate all this stuff. No problems, mate, it's going to be great. This is for reading, and this is register 0, and it really depends on what value, when you read this back, what value mode has. I've changed these up a little bit so that mode 0 is now off, mode 1 is the bitmap, mode 2 is BCD, and mode 3 is going to be the clock. And so if you read from the register set and you're in mode 0, you get nothing back. If you're in mode 1, you get the bitmap values. This is in register 0. So you get the bitmap values on the upper 14 or 15 bits, 15 bits of 0, and then the mode. If you're in mode 2, then you get just the mode, and if you're in mode 3, then you get the timer 24 in the mode. Similarly, when you're in mode 1 and you read now, you'll get 0 unless you're in mode 3, then you get the hours, minutes, and seconds. Otherwise, the only other choice you'd have would be mode 2, and then you're in BCD value. And note the use of the don't care situation here for making those comparisons. So the goal now is we have the bitmap controller working. I've got some C code waiting for me to type in a bitmap. But I need to figure out what that bitmap needs to be. So, for example, we have the 15 bits, and they're kind of divided up into cathodes and anodes. And on the cathode side, I've got bits 5, 4, 3, 2, 1, and 0. And on the anode side, I have 8, 7, 6, 5, 4, 3, 2, 1, and 0. This corresponds to A, B, C, D, E, F, G, dot, and then theoretically our colon. And this corresponded over here to digit 1, 2, 3, 4, 2, 3, and 4, and then the colon, and then the degree sign. So let's say that I want to turn on the digit 3. In the 7-segment world, that looks like this. And if you recall from our previous video, we said that was A, that was B, C, D, E, F, and then inside here was G. So that would tell me to make 3, I want to have 1 where the A is, 1 for B, 1 for C, 1 for D, 0 for E, 0 for F, 1 for G, don't want the dot, and I don't want the colon. And then let's say that I want to turn on just the second digit, so that would be 0, 0, 0, 0, 1, 0. And I can't easily type in binary in C language, but I can type in hexadecimal. And one hexadecimal digit corresponds to 4 bits, so 1, 2, 3, 4. That's one hex digit. 1, 2, 3, 4 is another hex digit. 1, 2, 3, 4 is another hex digit, and then one more makes one more hexadecimal digit. Turning this into hex, that's a 2, so that's a 2. There's a 0, or there's a 1, 2, there's a 4 and an 8. 4 and 8 is 12. And in hexadecimal, that's C. There's a 1 and a 2, that's 3. And there's a 1. So if I were to bring up the display and type in 13C2, the C program shifts that over to the left by 17 bits to line it up into the mode register, and sure enough, I don't know if you can see it on the display or not, but that's our proper display. And in fact, if I were to change this to be a 13C1, we would see that it moves over, and I could even do a 13C3 and turn on the first 2 digits. So that's the bitmap display, and that gives me some confidence that what we're doing here is working. So in the C code, this was what we did to do the set bitmap. I'll do our set BCD. Okay, so now here's our BCD version, and I'm going to do 1, 2, 3, 4. And sure enough, our 7-segment display is doing exactly what it should be. It's displaying 1, 2, 3, 4. All right, the next one to try is the time, and the time kind of works the same as BCD. So I'll just copy this code, but instead of so in the case of the this needs to be changed to be set time. So I can now do our set time, and I can ask for hours, minutes, and seconds. And hopefully this will work. So our time display is already showing our 1, 2, and theoretically I would need to sit here for another little bit of time for that to change. But let's go ahead and do the set time to be 1, 2, and 55, and we should only have to wait for another 5 seconds. Actually, we might have to wait for a long time. I never set the time period. So when we do our set time, the base 3 needs to be equal to 50 million. And the base 2 needs to be 50 million. So anyway, so there you have it. So there's a whole process of going through and debugging, doing some simulation, finding problems that aren't even your problems. That seems to be par for the course. This video has taken almost 9 hours to make, and I'm going to try to chop it down as tight as I can. It'll probably be like 15 minutes once I get all the ranting and raving taken out of it. Hope this was helpful. Hope it's not too discouraging. And good luck with your projects. And I'll make 1 or 2 more videos in this series to show how to debug with the ILA core, and then to actually work on a Linux device driver. So those will be the next 2 that are coming up.